Whenever a wave or a disturbance passes through a medium, it is affected by the constituents of the medium, because the excitations of the wave interacts with the constituents and then it propagates from one place to another. Now, these constituents and the wave quanta interaction are essentially governed by the underlying interaction that one considers for the wave propagation. So, what becomes important in this context is the transformation properties of the wave quanta under the continuous transformations as well as the discrete set of transformations. For the case in hand and what we are going to describe, we will more or less be focused on the discrete set of transformations that changes the magnitude and size of the wave excitations. When we started this discourse, we pointed out the importance of the frames of references and their state on the wave signals, and we saw that there is some symmetry called Lorentz symmetry for continuous change of the parameters of this symmetry generates boost and rotation, and that affects the wave's amplitude if it is a vectorial or tensorial wave. But it is not just that, there are certain discrete transformation also. So, how this particular quanta transforms under these discrete transformations is also important. To begin with, we start with the transformation properties of the gauge fields, and we outline their transformation rules following the conventions of quantum field theory by Claude Erichsen and Johannes Zuber. And it shows that under charge conjugation, the gauge fields pick up a negative sign. It is not very difficult to understand, because if we convert particles into antiparticles, then the current that was flowing by the motion of the particles will pick up a negative sign when we replace the particles by antiparticles. However, the demand is that the interaction J dot A current times the gauge field should not change under particles going to antiparticles. The equations should remain the same. So, if current change its sign to keep the whole thing same, the vector field that is concerned should also change its sign. That is what is given by equation number 66 that is presented on the slide. Similar considerations leads us to the other transformation rules, and they are how these vector fields transform under time reversal and parity inversion. They are given in 64 and 65. Given these properties, it is not very hard to find out the transformation properties of the field strength tensors under C, P and D, and they are given in the three sets of equations from 67 to 69. There is a slight departure in their transformation rule when you move from the gauge fields to the field strength tensors, but we should remember that there are extra derivatives, those are included in the definition of the field strength tensors. So, these are the two major sets of transformation rules, and these rules should be valid whether a gauge field is active or passive, it is external or internal. You should remember it as we go along. Now, having described the transformation rules of the dynamical fields, we are set to realize that if we have a situation when these excitations that we are talking about, or the propagation of the excitations we are talking about, happen to be taking place in presence of an external field, then instead of picking up a spatial geometry, we can try to construct a frame of reference by considering the system variables and talk of excitations in terms of these coordinates defined by the system variables. So, how do we do that? Okay, let us notice that if we have a field strength tensor that is given by F mu nu, if you contract it with a wave 4 vector k mu, then we generate a 4 vector which we have defined by B 1 of mu. So, what is the great property that B 1 mu satisfies? The B 1 mu satisfies a property that in 4 space it is orthogonal to the direction of wave propagation. And how does B 1 mu transform? Under T, if it is transforming, then we have to operate T B 1 mu T inverse, then write down the vector in terms of its components and find out how each one of them transforms. And then when we combine these things together, we get the final transformation rule for B 1 mu. So, as we see that under time reversal and charge conjugation, B 1 mu changes its sign, but with a difference that is the contravariant B 1 mu goes to covariant B 1 mu under time reversal transformation, whereas under charge conjugation it just picks up a sign. That is because under charge conjugation the field strength tensor points in the opposite direction, that is in the negative sign. So, that is where it comes from, and under spatial inversion it just goes from contravariant to covariant representation. The B 1 mu is not the only vector that we can construct in this method. Given the external field strength tensor, we can always create a dual tensor which is F tilde and employ the techniques that we had used earlier to generate another vector B 2 mu 4 vector. It looks almost identical except for the fact that it has a factor of half multiplied, and this half is to keep track of the overcounting. So, with this definition for B 2, the second vector, we go on to construct these 3 transformation rules, and they are right before our eyes is 74, 75 and 76. The other vectors, those needs to be taken into account, is something that I have defined by I nu, and why I have constructed or you have taken this I nu to be so different, or why you have brought it in. We have brought this particular vector in because though we had B 1 and B 2, those two are orthogonal to each other, both of them are perpendicular to 4 vector k, but there was another vector that you could construct using the medium velocity. They failed to satisfy this transversality condition with this medium velocity. And this vector u tilde that we have defined will, you can see that this particular vector is given over here. This is orthogonal to k, that means if we contract it, the wave vector, it turns out gives 0, but with other vectors it does not give 0. So, why it does not give 0? That can be traced from the equation here 97. If we are allowed to amend for this misprint of k mu here by a medium velocity u mu, then we will immediately realize that u tilde may be orthogonal to the wave vector k mu, but it is not orthogonal to B 2. So, we had to invent another vector I mu, so that that particular vector is orthogonal to B 1, is orthogonal to U tilde and is orthogonal to K mu. We will come back to this particular aspect later on, but let us first be through with the transformation properties for this vector that we have defined by I mu. So, to do that, what we need to know is the transformation property of the scalar products in 4 space, which are given here, and as I have shown that they do not go any more undergo any modification or change. So, with this and the transformation properties of U dot k, another scalar product which reverses its sign for 2 cases, but retains its sign for the parity inversion. The way this vector I mu transforms under time reversal is it becomes a covariant vector with a negative sign if we perform the transformation on the contravariant vector. If we do the parity inversion on the contravariant, it becomes a covariant one, and under charge conjugation, it just flips its sign. That is because this particular vector is linear in the field strength tensor that flips its sign under the operation of making the particles become antiparticles. And lastly, the transformation rules for U tilde vectors, I have shown earlier what U tilde stands for, are given by equation numbers 86, equation numbers 87 and equation numbers 88. So, being armed with these transformation laws, we have to now find out the scalar coefficients, those are necessary to expand a dynamical field in terms of its vectorial parts and the scalar parts. How does these scalar counterparts or the form factors, they change under this discrete set of transformations. Now, a priori, guessing how these objects, those are called the form factors, would change, but if we know how each component of the dynamical gauge field transforms under a specific transformation, for instance, under time reversal symmetry or space reversal symmetry or charge conjugation, then we pick up the component of the gauge field and write it in terms of these form factors and the individual vectors and apply this transformation, so that the left hand side and the right hand side. The example here is equation number 90 at the bottom. So, the transform under any particular transformation, the left hand side and right hand side should have their signs maintained. They should remain invariant. And if that is what we are demanding, then with the knowledge of how individual vectors transform under a specific transformation, be it P or C or D, we can assign the transformation rule for A parallel, A perpendicular and A longitudinal, so that a particular component of A, which is defined by A alpha, does not change its sign, it remains the same. The extra symbol that I have used here, N1, N2 and NL, does not have much role to play, because they are introduced to normalize these vectors B, I and U tilde. So, in principle they are quadratic under a square root sign. So, any transformation that you assign to them, it remain neutral. So, with this idea, the temporal component of the gauge field can be now written in terms of relation 91 or equation 91, and the spatial component of the gauge field now would look like equation number 92. And if we use what you said, the relations of 89 on 91 and 92, what we land up with are the transformation laws for individual form factors, A parallel, A perpendicular and A longitudinal, under the three discrete transformation that preserves the transformation law or rule for the gauge field, as well with when the necessary transformation law for the parallel, perpendicular and longitudinal components are properly accounted for. So, what we have done next is present before you a table, and this table essentially summarizes all the transformation rules for the dynamical fields, the vectors, the tensors, those are active and passive, those are encountered or they contribute to the propagation of a wave, be it electromagnetic, gravitational or QCD wave right before you. For simplicity, we have considered quantum electrodynamics, but it is not very difficult to generalize it to the other cases. When time comes and if it is encouraged, we will try to do that. So, with this flashing of this table before you, I would like to stop here and to the next important things that comes to cover the description of wave propagation in space time. Thank you.